I have 4 sentences and I have a question, and I want to see which sentence is closest to the question. So the first thing I do is count how many words overlap, and the first one wins. This is lexical search, and it's terrible because, as you can imagine, if I have sentences that look a lot more like my question, in terms that they overlap in a lot more words, but are wrong, then that the lexical search doesn't take care of that. For example, where in the world is my cup of coffee is lexically the closest sentence to where is the World Cup, but that's not the answer. So we need something much more, something that takes care of semantics, that understands the sentence and is able to tell even if the word doesn't have, if the sentence doesn't have the same words, if the meaning of the word is the same. So that's where semantic search comes in. And for semantic search, there's something called embeddings, which is the bread and butter of a lot of these models, but in particular of embeddings of semantic search. So let me tell you, if you haven't seen an embedding, let me show you what an embedding is in a very simple scenario. So let's say that I've managed to put words in a plane. So I have the words soccer, basketball, tennis, castle, house, motorcycle, car, strawberry, etc. And I'm going to ask you a quiz, and I have the chat right here. So I want to ask the audience a quiz. The quiz is, where would you put the word apple? And here are, for example, the coordinates of each word, horizontal and vertical coordinate. And I'm going to give you 3 options: A, B, or C. So audience, where would you put the word apple? In A, in B, or in C? I see someone saying C. Very well. Yep, everybody's correct. I see a lot of C's. I would also put it in C. And why would I put it in C? Because, well, the point of embeddings is that similar words are close by and different words hopefully are far away. So that's it. We have, and so the coordinates for apple could be 5, 5, for example. Could be a lot of things. Something else that happens with embeddings is the following. Check this out. Where would you put the word Rabat here? So we have Croatia, Morocco, Zagreb, and Rabat, which are the capitals, right? So the question is, what coordinates would you put for Rabat? A, B, or C? I'm ready for answers in the chat. Who votes for A, who votes for B, and who votes for C? Let's see. I see C again, C, B, B. Ooh, that's a close call. So B is not bad because it's close to Morocco, right? Rabat should be close to Morocco. But actually, I'm gonna go for C. And the reason is that these embeddings have sometimes a very particular interesting property, which is the parallelogram rule. And it just basically kind of captures analogies, right? Like Zagreb is to Croatia what Rabat is to Morocco. Or Croatia is to Morocco what Zagreb is to Rabat, right? So this in the same way that from walking from the word Croatia to the word Zagreb is the same as walking from the word Morocco to the word Rabat. So this capture analogies, and it also captures some kind of like small mathematical equations, like Rabat equals Morocco plus Zagreb minus Croatia. Why? Because, well, it's sort of like the computer starts understanding what things mean. So Rabat, let's say the computer understands that it's Morocco and capital, and Morocco, it appears as sort of Morocco and country, and Zagreb appears as Croatia and capital, and Croatia appears as Croatia and country. So if I do this math and I subtract, then what happens? Well, country and country cancel each other, and Croatia cancel each other, and I'm left with Morocco and capital, which is exactly what I have on the right? And you can see that this math works out in the coordinates. If I were to add things coordinate-wise, this equation holds. So embeddings are just very useful things because they basically take words and put them into numbers in a way that makes sense. See, words that are similar appear with similar numbers, and words that are far away, different, appear with far away numbers. Now here we have a very, very simple one with 4 words or a few words and 2 numbers per word. But in reality, we want lots and lots and lots of numbers for every word, and we want every word in the dictionary. The embedding one of the embeddings we have Cohere has 4,096 entries for each word. And this is basically a very good understanding of each word. But even more than word embeddings, we have sentence embeddings, right? So a sentence embedding actually takes each sentence and turns it into 4096 numbers. And in the same way as before, similar sentences are close by, and different sentences are far away, and a lot more stuff happens, right? So this is the bread and butter of everything. This is embeddings. I was playing around in this lab where you can actually see the numbers. So I'm gonna show you the first 10 numbers of a bunch of sentences, and so it's 4096, but I'm showing you the first 10, and we're just shading it to not appear as numbers, but the shading is in the value. You see it at the right. So notice that these sentences are all kind of similar, but in particular this sentence, show me a list of ground transportation at Boston Airport, and this one, show me Boston ground transportation, and this one, what ground transportation is available in Boston, are pretty much the same sentence, right? And notice that the embedding captured it. It said, you know what, I'm going to give you pretty similar numbers for those three sentences, even though the words are different, but it captured that these three sentences are very similar. So now that we have embeddings, then, and by the way, I have the chat in front of me, so if you have any questions, feel free to send them here, and I'll address them immediately, or right after. How to search. So now let me show you how do we use embeddings to search, and use embeddings to search. Like once you have a bunch of numbers to deal with, then it's much easier to deal with numbers than to deal with sentences, because you just do some basic math, right? So the way to do it is nearest neighbors. So let's say that we have our embedding. I'm gonna put it as two-dimensional. So I'm gonna pretend that it's two numbers per sentence, when in reality there's 4096. But let's, in order to visualize it, let's do two. And so let's say these are all your sentences, and now you have a question, a query. The query is, where is the World Cup? So you locate this sentence in the embedding, and then you simply just find which one is the closest sentence, the closest answer to that query. So see, having an embedding makes searching really, really easy, because then you get, the World Cup is in Qatar. Of course, there's difficulties, and there's many things, many technicalities that happen, and Nils will tell you more about it in his talk. But just I'm going to show you a small example. I was playing with the notebook, and I put these 8 sentences here. And so there's 4 questions and 4 answers. And these are the 4 answers. The bear lives in the wood, the World Cup's in Qatar, the sky is blue, and an apple is a fruit. And let's do a basic search. The search is, where is the World Cup? And what happened is that the embedding put it right here. And so that's the answer. And just to show you that the 8 sentences appeared here in the embedding, and you can see that each question, the closest thing to each question is its own answer. So I hope if there's any questions, feel free. All right, so now let me tell you a bit about similarity. So similarity is actually something that comes out of embeddings pretty easily, and actually it's a number that tells us if 2 sentences are similar or not. So here are my 8 sentences, and I have calculated the similarity for each 2 and put it in this table. So you see, like, light colors are close to 1, and dark colors are closer to 0. So as you can see, each word obviously has a similarity of 1 with itself, each sentence, and the answer tends to be close to the sentence. So for example, what color is the sky? And the sky is blue, have a similarity of somewhere around 0.7, and that means they're close in the embedding, right? And if I look at what color is the sky and an apple is a fruit, then it's close to 0. That similarity is probably not 0, but something very small. So that tells us that our embedding is something like this. And now let me tell you how to get similarity from an embedding. Okay, so the way to get similarity from there's many ways to do it. You can look at distance, because we're talking about high dimensional spaces, where you can do, like, Pythagorean distance or taxi cab distance, anything you want. But we're actually going to use one that's pretty useful, which is cosine distance. So this cosine similarity works exactly how you would imagine. We're going to look at the angle. We're going to say that the World Cup is in Qatar has a large similarity with where is the World Cup, because they're very similar. And where is the World Cup is far from the sky is blue, so they have small similarity. And so how do we find a large number between two close ones and a small number between the ones far away? Well, let's look at the angles, right? This angle between two close ones is a very small number, and this angle between two that are far away is a large number. And so we have to turn large number into small and vice versa. We're going to use the cosine. So this is the similarity between the World Cup is in Qatar and where's the World Cup is going to be cosine of the angle, and the similarity between where the World Cup and the sky is blue is cosine of the other angle. And why? The reason is because cosine is like this, and for a very small number, the cosine is a large number, whereas from a larger number, the cosine is pretty small. Let me know if there's any questions about that. I see some questions with Jacquard similarity work. Yes, I think probably Jacquard similarity will work. That's related to the dot product that is also related to the angle. Some questions like how will it treat the similarity between the sentences the man bit the dog and the dog bit the man? So yeah, that's something that if it's a good embedding, it will take care of it, right? A very simple embedding will probably not know the difference, but a good embedding that takes care of sequentiality, embedding that actually looks at the sentence's meaning and not just the words in it. So if in a good embedding, like you would see a difference between the man bit the dog and the dog bit the man. It would have them far away, right? But for example, it would have the man bit the dog very close to the man. Sorry, the dog bit the man very close to the man was bit by the dog, right? Yeah, any other questions? Okay. Yes, Saibu says, does the word order in a sentence affect embeddings? Yeah, a good embedding definitely captures word order in a sentence. So some basic models already do, like a recurrent neural network already captures the order of the words. So an embedding that uses context, that uses transformers and attention will definitely capture the order of the words. So just some things, some openers for the next talk. Yeah, the nearest neighbors is a pretty good algorithm, but it's actually not that fast if you just do it by itself, right? Like if I want to find what is the closest thing, the closest sentence to where is the World Cup, I would have to calculate pretty much all the distances with every other sentence in the space. This take time, and I actually would have to calculate all the distances between all the sentences. So if I had, this is a square, right? If I had 8 sentences, it's 8 square distances, and if I had a k 1000 sentences, a million, and in general is n squared. We don't want to do this. We don't want to be calculating n squared distances, especially if the number of sentences is humongous. And so therefore there are some solutions to this. One is inverted file index, which is in some way you cluster them, you group them around, and you have idea of what's neighbor, what things are close to one, so you sort of only look there. Another one is hierarchical navigable small worlds, which is, you have a huge set of sentences. Instead, you take just a few of them and find neighbors there. Then you add some more, and you have sort of a hierarchy of data sets, and that sort of gives you an idea of how to search faster. So I'm gonna tell you, I'm gonna tell you a little bit about what the embedding means in a multilingual search model. So the way it is I made some sentences, and I hope my French is good. My Spanish is definitely, I'm sure about that one, but I'm sort of 80 to 90% sure that those are my correct in French. But I use the Cohere embed model to actually embed them, not the regular model, but the multilingual model. The regular model will have them far away, but the multilingual model actually does this. It puts them pretty close, and the bear sentences are here, the soccer ones are here, the apple ones are here, and the sky is blue ones are here. So as you can see, the bread and butter of the multilingual model is that it not only sends similar sentences to points that are close, but it sends similar sentences in a bunch of different languages to points that are close. And that's one of the amazing things about the multilingual model. But now I'm going to obviously there are some difficulties with embedding and similarity, right? It's better than lexical search, but just doing this, just doing an embedding and finding the closest sentence may not be that great. I now put this small data set and I plotted it in 2 dimensions, the embedding, and notice that there's 4 points that are very similar. This one over here is where's the World Cup, which is the query. This one over here is the World Cup is in Qatar. This one is the previous World Cup was in Russia, and this one is the World Cup is in the moon. And notice that the embedding says these are similar sentences, right? They're all not lexically, but semantically similar. And the closest one says the previous World Cup was in Russia, which is very close, but it's not the answer. So how do you tell that it's the answer, right? So there's a lot more work to do this, right? Not just distance, but there's a lot more fine-tuning this model to make it good for search, to make it actually answer the right answer and not something that just happens to be a similar sentence. And so the question is, how can we make search better? And the answer is, stay tuned to the next talk by